Hello, good afternoon to everybody. We can begin. Please give me just the check that you can hear me and that you can see the shared slide, please.
All good.
Okay, perfect. So we consider the topics that we started yesterday. We began to speak about boundary layer. I recall the idea that Randall introduced more than one centuries ago to simplify the problem of the flow on a body, to take into account the effect of the viscosity in the fluid dynamic field. So I told you that if we consider the Navier-Stokes equation that are here reported in dimensional way, we want to simplify this equation. I just want to mention, because it's important for what we are going to discuss today and also next week, that you have to be aware that on the mathematical characters of this partial differential equation, the Navier-Stokes equation, if are considered as spatial systems, are elliptical, like Laplace or Poisson equation. And in particular, we have this ellipticity reflects on the problem of the boundary condition that we will discuss. We will see that passing from the Navier-Stokes equation, like the ones that are reported here, to the equation that refers to the approximation in boundary layer approximation, the character of this, the behavior of this equation will change, and from elliptical will be parabolic. This is very important from a numerical point of view, because you should know that if you have to solve an elliptical system, you have to give the boundary condition on all the boundary of the domain. On the other side, if we have a parabolic system, we can use a sort of marching algorithm, and so we can solve for a given value, for example, of the spatial coordinates, and then update what is going to happen step by step. So from a numerical point of view, there is a big difference in the solving. Okay, I told you that the general concept that are on the basis of the boundary layer is that the two terms, the left-hand side, the inertial terms, and the right-hand side, the viscous or diffusivity terms, have to be of the same orders. So this means that from the balance of these two quantities that are in terms of reference quantities, we have a sort of an estimation of the sides of the boundary layer. Remember that the boundary layer has been introduced taking by the observation that all the changes that we have along the x direction using this notation are much more slower than what is going to happen on the y direction. So if you want to catch, because this is the problem, what is going to happen in the y direction, the corresponding changes along the x can be neglected. So we have a slow and a fast variable. The slow variable is the x. So what is going to happen along the the stream direction, the x direction, will be very slow, and so we can almost neglect, not exactly neglect, but almost neglect, with respect to what is going to happen in the y direction, so the normal direction to the surface of the body surface. Okay, and the ratio between these two scales is related, the ratio is related to the Reynolds number in terms of the square root of the Reynolds number. So the accuracy of the approximation will be more correct, will be more accurate, this approximation, if the Reynolds number is quite high. So actually, for high value of the Reynolds number, we spoke yesterday about 1 million, we can say that, okay, it's correct to split, as we will see, the two scales, and so to neglect, where it is possible, the changes along the x direction. I want to mention here, but I will come back to the next observation, that sometimes if you have a strong change, a very fast change in the x direction, from a theoretical point of view, in that region where some quantity is going to change very quickly as a function of the x coordinates, in that region you cannot apply the boundary layer. So we should pay attention on this point, because sometimes we apply the equations that are obtained after the assumption of different scales, but we sometimes apply also in a region where actually the changes are of the two changes in x and y are of the same order of magnitude, okay? So before discussing the equation, I'd like to introduce the different way to define the thickness of this boundary layer. Usually you will find on almost all the books that one possible definition is the distance from the wall where actually you reach 99% of the external velocity. What I mean with external speed? External velocity means the velocity that you will find very far from the body, and where the effect, the influence of the viscosity can be neglected. Okay, so pay attention because this is important. This first definition is, as it is written in the slide, it is arbitrary because there is not reason to choose 0.99, not, for example, 0.19 or 0.9999. Okay, it's not a physical definition, but sometimes it's adopted. You can say, okay, when the difference between the external velocity is just 1%, I should say that I am out of the boundary layer, okay? But this is something that it is not so used in the technical papers because it's arbitrary. So if I want to make comparison between results on my analysis, experimental or numerical, with other results for the same geometry, for example, actually we have to compare quantities that are not related to an arbitrary definition. Okay, so this is the reason why a more physical measure of the thickness is reported here and is named the displacement thickness, that is defined with this integral. Okay, if you rewrite this integral in such a way, what you are going to evaluate with this delta star is a physical effect. The physical effect can be explained in such a way. Now imagine that we want to, this is the surface of the body, okay? So imagine that we do not have boundary layer, and we have an external flow which is coming with this direction, okay, parallel to this flat plate at an incidence which is equal to 0. The streamline, if you neglect the boundary layer, will be just straight lines that does not will feel the presence of the flat itself. Okay, so if I plot, for example, two different streamlines, the streamlines are all parallel between them. Okay, this is without the boundary layer effect. Okay, if instead we have the boundary layer, we know that the distribution in terms, for example, of velocity will be something like, will be something like this. Okay, for example, so starting from 0, we will go to the external value of the velocity, which we can write as u, as I named u here. Okay, and so also the streamlines will be different. The streamlines, for example, will be not parallel, but will be approaching to the slide, to the flat plate. We know that the streamlines will be something like this one. Okay. For example. Okay. So what is going to happen is that if we remember the physical meaning of the streamline, we know that between two streamlines, the distance from the two streamlines, if we introduce the stream function and we quantify the corresponding value of the stream function on the each streamlines, the distance from two streamlines is proportional to the mass flow rate between them. So what is going to happen is that if we take into account the boundary layer, okay, for a given distance from the wall, after this effect of the boundary layer, we will have a lower mass flow rate with respect to the case where the boundary layer is neglected, okay? So this is the sketch. So we have a velocity defect to which corresponds a loss of mass flow rate. And this quantity here, the integral without the box, is on the right-hand side, is exactly this effect, because if you multiply for rho here, you will have that rho, the integral from 0 to infinity of rho u dy, is the mass flow rate. U is constant for a velocity that is constant with y, okay? The actual mass flow rate actually is given by rho, the small, the lowercase u, the y, okay? So these terms here, which is reported here, okay, is a terms which is a measure of the difference in mass flow rate through a given section, okay? What we have without boundary layer minus what we have with the boundary layer, okay? So is a measure of what we are going to lose with the presence of the boundary layer. So we name this delta exactly the distance of which we have to move the streamlines to take into account this difference, this defect of mass flow rate. Okay, so as you see, the displacement thickness, and displacement refers to the move, the change in the position of the streamlines, is related to the imbalance of mass that is different with and without the effect of the boundary layer, okay? So it's a physical measurement, okay? By the way, for a flat plate at zero incidence, it is a problem that we will discuss in details. The value of delta for 0.99 definition, the thickness, is around 5 for these quantities, which is always the same. Instead, for the same problem, delta star for this same flat plate at zero incidence is around 1/3 of this one. So different definition of thickness will give different value of the thickness, okay? So in general, the displacement thickness is the most used, most adopted. Another possibility is not to work on the mass flow rate, so to make a balance of mass, but to make a balance of momentum, because also for the momentum, there is a difference in the flux of momentum with or without the boundary layer. Okay, so there is a question on the meeting chart. I do not understand the concept of displacement thickness. Okay, to give an answer, first I make questions. Do you understand the physical effect that the presence of boundary layer, as you see, we have a region where the velocity is lower of the external one. So the mass flow rate in this region from 0 to this value is lower with respect to the case where the velocity is always u. This is clear for everybody? Is clear also for you? Okay, so if you understand this point, this means that the streamline will change if we have the flow without boundary layers, the potential flow, or the flow with the boundary layer. And the movement, the displacement of these streamlines is exactly related to this quantity, okay? The displacement thickness is, you can measure in how much you have to move far from the body to have the same mass flow rate, okay? Is without the boundary layer, you have a given amount of mass flow rate at, for example, 1 centimeter, okay? To have the same mass flow rate, you have to displace this point of a given quantity, which is delta star, to have the same mass flow rate. This is the reason that the delta star is named displacement, okay? So you have to measure at a distance which is a little bit bigger with respect to the previous to have the same flow rate as it is written here, okay? Following the same physical concept, if you measure the change in momentum here without a boundary layer and boundary layer, you will have a difference. And again, this difference is measured with this integral here and is proportional to this quantity. So theta is the thickness that you have to consider to have the same value of not mass flow rate, but momentum flux. Remember that the momentum flux is a vector quantity. If we want to measure the flux of momentum along the x direction, you will have to obtain the mass flow rate times the velocity in the x direction, okay? And so you have this definition, okay? So, in summary, displacement and momentum thickness are physical measure of the effect of the presence of the boundary layer, okay? And are not related to any arbitrary definition. If you speak and report the displacement thickness for your problem, there are no ambiguity. So another researcher in another place of the world, if want to make a comparison, he knows that to evaluate delta, this is the unique expression. Otherwise, you have to define 0.99, 0.998, or for example, 0.9, and that's all. But it's something that is not related to the physical behavior of the flow. Okay, so the three definitions are important, you have to remember, okay? An additional concept is, if we know, and up to now we didn't spend time in describing how to solve the equations, but imagine that you solved the boundary layer that you have still to obtain. You can evaluate what? You can evaluate the shear stress at the wall, which is usually named the friction, okay? So this is a Newtonian fluid, so the shear stress is related to the dynamic viscosity times the normal derivative, the normal gradient, evaluated at the wall. Okay, so this is the shear stress at the wall. By definition, if you make the integral, like it is written here, if you make the integral of the shear stress, you will have the friction component of the drag. Exactly like if you make the integral of the pressure distribution in the x direction and project in the x direction, you will have the drag components due to, for example, to the distribution of pressure, if you have not a symmetrical distribution of pressure. Okay, so remember that the aerodynamic force is usually related to the integral over the surface of the body of shear stresses and pressure. Okay, if we again speak in terms of order of magnitude, we know that the reference quantity for the u component, the x component of the velocity, is named, for example, u0. The y component has as reference quantity, so this length has as reference the delta, which is the reference length, is the thickness of the boundary layer. Okay, so this ratio is infinity over delta, but we know that delta, we obtained here, is related to the Reynolds number. Okay, is related to the Reynolds number through the square root. Okay, so we can write, copying that equations, that the order of magnitude of tau will be given by the square root of the viscosity, dynamic viscosity, the density, the external reference speed to the third power, okay, over x. This is an inequality not strict. So changing the problem, changing, for example, the shape of the body, the dependence will be always proportional to this quantity, but you will have a coefficient in front of this equation that will be different for if you change the problem, okay? And exactly like delta will be always proportional to the square root of x, okay? What will be different, as you see here, 5 over 3, here will be lower, much lower than these terms here, but in any case, all the displacement thickness, so all the thickness of the boundary layer, all the value of delta, will be proportional to the square root of x. Tau will be proportional to the square root of 1 over x. This means that, for example, if you have a airfoil on the leading edge for x, which is equal to 0, where you have the origin of the boundary layer, you will have that tau will be singular, will diverge because will be 1 over the square root of tau, of square root of x, okay? Is it clear up to now? Okay, if is it clear, we can go on and we discuss this table, which is interesting because we understand immediately when it's correct to say that delta is different from L, okay? So, for example, we know that for water and air, the viscosity, dynamic viscosity, and kinematic viscosity are of this order of magnitude. In particular, for air, we know that, for example, the viscosity, as you see, is function principal mainly of the temperature. And moreover, you can appreciate that if you are working with a liquid, water or air, the dependence on temperature is completely different. If for water you are going to increase the temperature, the viscosity, the dynamic viscosity, will decrease. On the other side, if you deal with a gas like air, you see that the dynamic viscosity will be higher, will increase. Okay, this is related to the molecular model that are different for liquids with respect to gases. Okay, but neglecting for the moment the effect of the temperature, we see that the order of magnitude of the viscosity is around 10 to minus 6, okay, 10 to minus 5 for air in particular, okay, 10 to minus 6 if we are working with the kinematic viscosity of water. Okay, I'm interested in this table. For air, we will speak about air because we speak about the flow over a wing. If we have 5 meters, for example, of characteristic length, which is the typical value of the, for example, of a quite big aircraft, okay, and 100 meters per second, which means 360 kilometers per hour, okay, so it can be also higher. The Reynolds number is around 10 to minus 7, okay, so 10 to minus 7, if we perform the square root, we have that in terms of millimeter, we are 30 millimeter, okay? 30 millimeter means that we have to compare, for example, 10 millimeter, so 1 centimeter with 1 meter, okay? So the effect is important, okay? Is it clear? So, as I told you yesterday, if we have 1 centimeter, for example, okay, there is a question concerning what I'm trying to explain is that we use, if you just spend 1 minute on this table, you see that the ratio between delta and L, which is the characteristics length, is actually small if the Reynolds number is quite large. If the Reynolds number is 10 to 6 or 10 to 7 or 10 to 8, we are in the right position to say that delta is much smaller of L, and so it's correct to split the two quantities. If the Reynolds number is 1, the two values will be the same because are related by this equation here. Okay, delta over L is, this is of order 1, as we said yesterday. Delta over L will be 1 over the square root of Reynolds. This is approximately, because is not just for a comparison of order of magnitude, not exactly 1 over the square root of Reynolds. There is a coefficient that can be different. So this means that the difference is important, is significant, if the Reynolds number, it is quite large. Okay, is clear now? Is it clear? Okay, I mean with the splitting of, not the two effects, I don't know if I said effect, it is wrong. We can split the two scales. So we can split what is going to happen in the X direction from what is going to happen in the Y direction. This number says that, okay, our boundary layer thickness will be of the order of 10 millimeters. So in 10 millimeters, all the important things concerning the viscosity will be happened. Instead, if you want to see some changes along the X direction, we have to wait for 1 meter. So the changes of all the physical quantities, the U, the pressure, in the X direction will be over a scale of 1 meter. The same changes, the E, the velocity, the pressure, all the things that we are interested in will be on the order of 10 millimeters in the Y direction. This means that we can split the two scales, okay? And the splitting of the two scales, so the introduction of delta and L is justified only if the Reynolds number is quite large. Otherwise, if I have that delta and L are of the same order of magnitude, I'm not justified to split the two scales. Okay, now it should be more clear obtaining the results. As you see here, from the equation of the Navier-Stokes that are reported here, these are the dimensional equation of Navier-Stokes. Here, if you make the non-dimensionality, make the equation non-dimensional, you will find that X and Y has to be referred to the same quantities. Okay, in particular, how you make this quantity here non-dimensional? You multiply for U0 and divide for U0. You multiply this term for U0 and divide for U0. You multiply for L and divide for L. The quantity referred to the U0 and L are non-dimensional. What you have in front of this term will be the square of U0 over L, which is exactly what is written here. Okay, if we use the L as reference frame. The same is true also here. We multiply by U0 and divide by U0. Here we multiply by the square of L and divide by the square of L for these terms. But in Navier-Stokes, we have a unique scale, so also Y will be multiplied by the square of L and divide by the square of L. We will see that this is not more true if we have two different scales, L for X and delta for Y. Okay? So we can, at this point, discuss this passage, this step. As I told, here we have the Reynolds, not the square root of Reynolds, because these are the Navier-Stokes equation. And if we introduce this reference quantity and reduce this equation in terms of this reference frame, for example, here we will have the pressure, we will have a rho times the square of U over L. So in front of the gradient, we will have this term. In front of the diffusive term, we will have, okay, I write, we have the P over the X, which becomes rho times U0 square over L times the, let me name the P prime over the X prime, where P prime is P over, then I show you what I'm writing, rho U0 square, and X prime is X over L. Tell me if you can. Can you see what I'm going to show you?
Sì, sì.
Okay. As you see, I multiply and divide for the same quantity. Okay. Now, if I repeat the same procedure for the diffusive term. So I have the second derivative of u over 2 times x, so over x squared. I have to multiply for u0 and to divide for the square of L, okay? And so this second derivative becomes u prime, the second derivative of u prime with respect to x prime 2 times, okay? Where u prime, like before, is u over u0 and x prime is x over L. Okay, so the two terms becomes the right-hand side. Okay, let me write the right-hand side. It will be minus rho, the square of u0 over L. Then I have the gradient of pressure in non-dimensional terms, plus what I have in front of the diffusive term. I have u0 over the square of L times mu, because there is the dynamic viscosity, okay? The reference mu. Also, mu is referred to the reference viscosity, times the second derivative of x, of u prime over x prime. Now I will show you what I'm writing, okay? So this is the, let me show you, then I will upload this, what I'm, okay? Can you see?
Sì, adesso sì.
Okay, okay. So now I should repeat the same procedure for the left-hand side, but you will find that on the left-hand side you will have the rho, which is the reference, the density. So you will have rho 0, rho prime, which is rho over rho 0. Then you will have u0 over L, okay? This is the terms that multiply the convectivity. So u prime, the u prime over the x prime, okay? And so if I divide everything for these terms here, okay, the coefficient of the left-hand side, I will have exactly 1 over Reynolds, because it should be u0, mu0 over the square of L divided rho u0 square over L, okay? And so it will be mu over rho u, and now I'm going, which is 1 over Reynolds. And now I show you what I have done. Okay, just look on the final part. As you see, this is the way we make non-dimensional the Navier-Stokes equation, and as you see, you will find in front of the diffusive term 1 over Reynolds. Okay? Is it clear?
Okay.
Okay, everybody can see what I'm going to show on the camera? Also the other students? Okay, if someone has problems, please write me, okay? Okay, this is for Navier-Stokes. Now, we have to repeat the same things for boundary layer. What is the difference? The difference is that we have not the one unique scales. Here, the scales in L is named 1, okay? And this is delta star. So as you see, if we use this L over U0, L, U0, and U0 as reference quantity, like in the Navier-Stokes, we will find for U and for T, 1, this ratio. This is of order 1, it should be U0, okay, order 1. U0 over L, which is of order 1. Pay attention because V, the velocity, the vertical component, the normal component of the velocity, is not of the same order of U. And why we have these two scales? Is a consequence of the continuity equation, because if we have that the U over the X is of order 1, and we know that Y is of order delta, if V should be of the same order of U, you should have here 1 over delta. And so you should have the two terms of the continuity equation that should be different, very different. In particular for delta, which is very small, you should neglect this part, okay? Which is something that it is not correct, okay? Because we are saying that the changes along the X are slow, but are not equal to 0, okay? So from the continuity equation, we found that if delta is the scales of Y, delta is also the scales of V. And this is why in the third terms of the second terms of the convective part, so V times the U over the Y, we have 1 over delta, because U it is of order 1 and Y is of order delta, but also V is of order delta. So these terms here is delta over delta, it is 1. So it's of the same order of magnitude, this one. Okay? So the left-hand side, everything is of order 1. On the right, the P over the X is of order 1, and so it is like all these other terms. What is going to happen is that Reynolds, 1 over Reynolds, is of order delta squares. We know that delta is proportional to 1 over the square root of Reynolds. So the square of delta is 1 proportional to 1 over Reynolds. Okay? This terms it is of order 1 because we have U and X. Okay? The important difference is that the second derivative of U with respect to Y 2 times is of order 1 of delta. So if I multiply this delta square for the two diffusive terms, I will have one which is of order delta square, another one which is of order 1, because these terms will simplify with this one, okay? So at the end, all the terms in this equation are of order 1, except these terms here, which is of order delta square. And so this is why, if delta is very small, it's much smaller than 1, we can say that these terms can be neglected. So the boundary layer approximation will lead to the cancel of these terms for the X direction balance of momentum. Is it clear? I should imagine that you already have studied in the past how to obtain the boundary layer. There are different ways to arrive to the boundary layer. I think that this is one of the most simple, because it's just a matter of we have just to make an analysis of order of magnitude, and we see that all the terms are of the same order except this one. Delta for large Reynolds is very small, and so we are justified to cancel this derivative. So the approximation of the boundary layer for the x direction, the balance of momentum in the x direction is just the same like Navier-Stokes without this term. Okay, a little bit different is the momentum equation in the y direction. As we see, we have a terms of order delta here, here, and here. Okay, here this is of order 1 over delta, so I should write here 1 over delta. Here it is delta star, like before, delta and delta star. So if we multiply, we have delta here, so here it is delta, and here it is 1, sorry, here it is delta cube, and here it is 1, it is delta, okay? If we multiply these terms for this, okay? So we have delta, 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 1 over delta, delta cube, delta. So for delta small, the unique term that will survive is this one. So if we use that delta is small, we obtain from the momentum equation in the y direction that the most important terms, it is the derivative of p over y equal to 0, because all the other terms are of lower importance, smaller order of magnitude, are delta or delta square, and so are very small with respect to 1 over delta. Remember that if delta is small, 1 over delta is large. Okay? Is it clear, this point? Because we obtained that the continuity equation is exactly like Navier-Stokes, so are the same. The momentum equation in the x direction is proportional, is equal to Navier-Stokes except for the terms du over dx square. So just the diffusive term is a little bit different. The momentum equation in the y direction is completely different because we have just that the gradient in the y direction of the pressure is equal to 0, and that's all. This analysis has important consequence. Exactly. Now we arrive to the comment of your colleague, because the p over the y equal to 0 means that the p over the x is not a partial derivative, but an ordinary derivative. This means that p is not a function of y, but only of x. In particular, if it is not dependent on y, you can evaluate for the value of y that you prefer. In particular, you can evaluate the pressure also from the solution out of the boundary layer, so the solution of the Euler equation. Okay? So this slide describes that in particular we have 1 over Reynolds here. Okay, if we change the y from y to y with the line hat, so the line over reported here, the new variable will be such that in this new variable, so the new y and the new v, the Reynolds number will disappear from this equation. And this is important because, as you see, the boundary layer can be written in following this change of variables in a way that is not dependent on Reynolds. This is not possible with Navier-Stokes. So what is important is that with the boundary layer, you can solve just once the set of the equation, and then using this expression, you can put in the post-processing the effect of the Reynolds. So you solve this set of equations where you do not have any parameters. On the other side, in the Navier-Stokes equation, this is not possible, and you have to make a numerical integration for a given value of Reynolds. If you want to see the flow for a different value of Reynolds, you have to repeat the numerical integration. Okay, this is important because the Reynolds number can change dramatically the effect on the fluid. But with Navier-Stokes, you have to repeat many simulations if you want to see the effect of the Reynolds. With the boundary layer, this is not necessary because you solve this set of equations, and then if you want to see the effect of the Reynolds number, is just a sort of rescaling the y and the v. Okay, you rescale y and v, so what is going here depends on Reynolds in such a way. Is it clear at this point? This is fundamental because also from a numerical point of view, you have just to carry out just one numerical integration. You can do very accurately, and then if you want to see the effect of the Reynolds, you have just to scale the y and the v. Okay, I repeat, with the Navier-Stokes, this is not possible. If you want to study the flow at Reynolds 1000 and then at Reynolds 5000, you have to repeat the analysis. Okay? Okay, we go on. These are the consequences that we already discussed. The p over the y's are equal to 0, so the p over the x is an ordinary different derivative. The pressure is given, as it is written here, by the external flow. This means that the pressure is not changing inside the boundary layer. And so you can use the Euler equation. This is correct because, as you see, this is an equation that you are going to, the set of differential equations are just two, and the unknown variable are u and v. So actually p is not more something that has to be solved as part of the boundary of the differential equation. It's not more an unknown quantities. Remember that when you approach to the boundary layer, from a theoretical point of view, you already know the Euler solution. Okay, so you already know the external solution. So if you want to study the flow around an airfoil, around a wing, you first have to solve the non-viscous problem. You have to solve the Euler equation, so you find the solution around the wing without viscosity. Okay, then you can introduce the boundary layer, and what you are going to change is that instead of having the impermeability condition, you will have the adherence condition, the no-slip condition at the wall, and what is going to happen is that you are enlarging the closed region very close to the body to expand and to see the effect of the viscosity. But you have to know already the solution of the external flow, so the solution where you neglect the viscosity. So in this sense, the pressure is something that you already know, because what is reported here on the left-hand side is something that you already know. So you have just to put these terms inside the equation here, but it is a known term. Is it clear? Okay. Okay. We go on. Boundary layer equation. The condition that we have to give. Pay attention, because this is something that I will repeat, and you are recording, so remember, because it is also recorded, that I will almost for sure I will ask at the exams. So the change that we have done in the equation, okay, apart from this particular nice effect of losing the explicit dependence of Reynolds, we are going to change the character, the mathematical behavior of the equation. And so also the boundary condition will be different. In this set of equation of this one, we have to give the boundary condition on U and V for X and Y. In particular, if we look to the diffusive term, we have to give two conditions on U for the variable X, two conditions on U for the variable Y, because these are the higher order terms in the derivative, two conditions of V and two conditions of V for respectively X and Y. Okay? This is important. Okay. Now, our set of equations are this one. The higher order equation in the U is just for Y. The derivative of U with respect to Y is second order, but the derivative of U with respect to X is just here and here, so 1. So here we have to give two boundary conditions for the variable U with respect to the coordinate Y. One boundary condition for the variable U with respect to the coordinate X. Okay, for the V is not more present on the second momentum equation. So we have the derivative of V only here in this term. So we can just give one boundary condition with respect to the V, for the V, with respect to the, oh, sorry, okay, with this for the coordinate Y. V is not derived with respect to X. It should be here but disappear. So we cannot give boundary condition on V with respect to X. And moreover, we can just spend one boundary condition on the V, the normal component, with respect to Y. So pay attention, because if I'm saying that at the wall Y equal to 0, both the two components of the velocity will be equal to 0, I already spent the unique condition that I can give on the component V. Okay? Instead, for the X component of the velocity, the component U, actually I can give another boundary condition, and so I can give the condition that for Y, which goes to infinity, we connect to the external solution. So we have U that goes to the external value of the U, so the Euler solution. But for V, this is not true. So if I have that the flow out of the boundary area is parallel, so the external value of the V is 0, we do not have this in the boundary condition, because we will not find that V far from the body will be asymptotically equal to 0, because we cannot give to the equation. So this is important. So these are the conditions Y. Take into account that the equation is also derived, the U is also derived with respect to X. So we should also give for a given value of X, this is something that depends on the physical problem, on the odd geometry, a condition on the U with respect to X. Is it clear? Because this is something fundamental. Okay? Okay. If we know the solution, we can evaluate the shear stress at the wall, we can make non-dimensional this shear stress, and so as we introduce the pressure coefficient, we introduce the friction coefficient, okay, which is a function that is, as we know, function of the Reynolds number, okay? The condition where we have separation we will discuss, I don't know if today or tomorrow or on Tuesday, is given by the u over the y. Okay, so you can write dimensionally or non-dimensionally are the same. The condition where you will have the separation of the flow will be equal to the u over the y equal to 0. Okay? I will show you an analysis where you can recover these third results reported in these slides. Okay, I will skip. This is a proof that the external flow on the V is not usually recovered by boundary conditions because no condition can be given for V. And so what we will find, you can follow this step, is that far from the body, the value of the velocity will be different, will be different from 0. This difference is not asymptotically going to 0. So if the external value of the velocity is 0, you will find something which is not equal to 0. Obviously, the mistakes, this is a mistake. This disagreement is of order 1 of square root of Reynolds, because the value of V is related times the square root of Reynolds. So if Reynolds is okay, the mistakes will be small. For example, if we have, can you hear me? Because I have a message of bad network quality.
Yes, Professor, there were some interruption, but right now it's okay.
Okay. So if we have the external velocity V, which is equal to 0, we will find something which is not 0, but it is of the order 1 of square root of Reynolds. Okay, so if the reference speed is 1 in the x direction, what you will find for the V components far from the body will be, for example, 10 to minus 3 if the Reynolds number is 10 to 6. Okay, so again, the approximation is more accurate if the Reynolds number is large. And also the disagreement that we have will be smaller if the Reynolds number is a big number, is a large number, okay? Okay. These are considerations that we already have done, okay? Another point that I want to stress here is that pay attention that the left-hand side of the X momentum equation is exactly equal to the Navier-Stokes equation. So if we started from a nonlinear problem, we still have a nonlinear problem because the convective term is still present in this equation. So what is going to happen, you can ask, but where are more simple the boundary layer equation? Are more simple in the fact that apart that we can neglect pressure because is something that we know. But the other point where we have a simplification with respect to the full Navier-Stokes equation is that missing this term is possible to have the universal solution and that we can solve for a given value of x, so we can fix x, solve for y, and then we can repeat the analysis for a new value of x, again for y. So it's the so-called marching algorithm, the marching step. So we can split the solution in x and y, okay? Due to the splitting in the two scales, like we said before. Okay. Now we go to the last 2 points, vorticity. If we have an external flow which is irrotational, so we have a potential flow, so without vorticity, the presence of a boundary layer will introduce vorticity. And this is immediately possible to evaluate just if you look, for example, to a small element close to the surface. Imagine that this is the surface. So, okay, this is the body, and this is an element that we move. If we evaluate the vorticity on these terms, we will find that it is different from zero, because here it is zero. If you make the circulation around this body, which we know is proportional by the Gauss theorem to the vorticity, the flux of vorticity here. So if we make the circulation, we will have that these terms is equal and opposite to this one, the vertical velocity. This will be different from zero. This will be different, will be equal to zero. So the circulation and so the vorticity actually is different from zero. In particular, if the fluid is a plane flow, we have just one unique component, and in particular, at the wall, the vorticity can be evaluated like the u over the y. So exactly the vorticity is related to the shear stress at the wall. Okay. In particular, the change of vorticity at the wall, the derivative of the omega over the y, is related to the gradient of pressure. And I remind that the gradient of pressure is something that it is related to the external flow. Okay. In fact, these are the last 3 slides important. With the presence of the boundary layer, we can immediately understand what is the effect of the external pressure gradient. If the pressure gradient is favorable, this means that the P over the X is less than 0. This means that we have a decrease in pressure as we move towards increasing value of X. Okay, so we have something that is going to push our fluid in the X direction. We have that, remember that we are writing the equation at the wall. So if we write the equation here, the momentum equation at the wall, in the linear, in the steady case, these steps disappear. At the wall, U and V will be equal to 0. So this equation written at the wall says that the pressure gradient is equal to the diffusive term. So as it is reported here, the pressure gradient is related to the derivative of the shear stress, or in other terms, to the derivative of the friction coefficient, if you put in non-dimensional way. So this is important, okay? In fact, if the P over the X is negative, also the derivative of the shear stress at the wall will be less than 0. So you have to read this equation starting from this picture here. Okay, we know that for the P over the X less than 0, so a pressure gradient which is favorable, we start from something which is less than 0. We know that out of the boundary layer, the shear stress has to go to 0, but constantly. So not only the shear stress, but also the derivative of the shear stress. So the second derivative of the u over the y goes to 0. Okay? If we pass to the second derivative of u to the first derivative, we have a shear stress which is positive, then far from the wall it goes to 0, and goes to 0 with the same sign. So starting from a positive shear stress, we arrive to 0 with all positive shear stress, because we know that we do not have a change of sign. The derivative is always negative. And so we know that the profile, the distribution of velocity as a function of y is something that it is with the same second derivative. So the concavity is constant. We have no change of concavity. Okay? Is it clear? Do you understand this set of steps? Because this is easy, because all has the same sign. Negative pressure gradient, negative second derivative. So everything goes smoothly to zero. Okay? Give me a feedback, because this is important. Okay? Okay for everybody? Okay. Okay. Now we move to the opposite part. Imagine that we started from a favorable pressure gradient on the leading edge of the boundary layer. Then the flow, due to the dp of the x, which is less than 0, is going to accelerate. Okay. Then you have the inversion. You will have a point where you have to recover pressure. So you will have a dp over the x that has to be greater than 0, positive, because you want to recover the pressure. Okay, the pressure is going to increase along the x instead of decreasing. This means that also the u over the y is positive. Okay, so the distribution of the derivative of the shear stress, so the second derivative of u over the y, will start from positive value, but necessarily you should have to go through a 0. Then you have to go to 0 far from the body. This is necessary because we have that the u over the y, we start from a condition where the u over the y is positive. We just changed the pressure gradient is positive. So at the beginning, the shear stress has to increase because its derivative, this is the shear stress, its derivative is positive. So at the beginning, you see that the derivative is positive here. Okay, this is the slope of the shear stress, which is given by this number. But we know that far from the body, the shear stress has to be 0. So there should be a maximum. If you have a maximum for the u over the y, you should necessarily need to have a 0 for the derivative of the u over the y, which is the second derivative of the u over the y. So you have a maximum, which corresponds to the 0, and then you go again towards 0 as the second derivative of u. Okay? In terms of velocity profile, this means that, as you see, you have the second derivative, which is positive, and then negative. So you have a change in concavity. Here the concavity is in this direction. Instead, here it is always the same sign of concavity. So you have an inflection point here where you have the 0, and then you recover the behavior that you have also here, going to the external value of the speed. Okay? As far as you proceed, the adverse pressure gradient will reduce the value of the shear stress at the wall. If you reduce, there will be a particular value along the pressure, along the surface of the wing, where the u over the y, so the shear stress, will be equal to 0. This means that this point I, the inflection point, will move to the surface. Okay, and so in this point, you will have that the inflection point is in this point. It is here. If you proceed further, what you will have is that the u over the y will go to negative values. And so you will have a part of the flow where the direction of the velocity will be opposite to the external one. And so you will have a separation, okay? As reported in this sketch, which is a summary. So you start from positive favorable pressure gradient. So as you see, the distribution of the velocity has always the same concavity. Then from this profile to this one, the difference is that here the P over the X is not more negative, but it is positive. So something is going to happen, and so the velocity will have different sign. In the separation point, this inflection move here at the wall, and this is the point that on the left you have still positive velocity, parallel velocity close to the wall. If you make a section here, as you see, there is an inversion in the direction of the speed of the velocity. And so after the separation, you will have a bubble, because you have a region where the, here, let me plot in such a way, okay, here the direction of the velocity is inside is reported here. Out here, the velocity is in the opposite direction. Okay, and so the point where you have the u over the y equal to 0, so the point where you have the vanishing of the shear stress is the point where you will have separation. In principle, you cannot proceed further or with the boundary layer approximation, because in this region, as you can imagine, the changes along the x direction are of the same order of magnitude in the changes along the y direction. So this is why the boundary layer equation and the boundary layer approximation as a conceptual tool cannot be applied to flow which are separated. Pay attention, because if you have a code, you can push the integration also after, behind this point, but what you are going to obtain is something that it is not correct, because it's the hypothesis that you have on the basis of the approximation that it is not more fulfilled. Okay, so remember, this is what I said at the beginning. The approximation is correct if the two scales are different, because as you remember from what we have done just today, we split the two scales and we neglected part of the equation, assuming that delta is smaller than 1. But if, like in this case, the changes along x are of the same order of magnitude of the change along y, this is not more true. So the boundary layer equation cannot be adopted to study flow separation of flow. For example, the flow around a cylinder cannot be studied with a boundary layer equation. You have to study by Navier-Stokes for all the value of the Reynolds number. Is it clear? Because at this point I will stop. But I just condensed in one lecture something that maybe you have done in the past in more than one lecture. But it's important for me that you fix on all the main points of the boundary layer. The point where we started the hypothesis and the main properties of the boundary layer. Next time we will see how we can use the boundary layer to obtain an analysis of the drag, okay? In particular, the friction. Have you got questions? Okay, as usually, I will stay connected for other 5 minutes. Then if you do not have questions, I will leave the meeting, and we update to the next Tuesday. Bye-bye to everybody. Sorry, there is a question. You asked if for the boundary condition, when y is 0, y 0 means at the wall, how can we deduce that u is also 0? It's not something that you deduce. It's a condition that you give. You say that the velocity of the fluid at the wall is the same of the wall. So if the wall is at rest, also the fluid has to go to rest. It's something that you impose, not deduce. Okay? This is a general rule. The boundary condition is something that you give because you want something. The problem is that sometimes you have to pay attention that you can give only the correct number of boundary condition. So, for example, we want to recover the external flow. So we say to the solution, okay, we found the solution such that far from the body we found the external U, and this is possible. Unfortunately, for the boundary layer, we cannot give the corresponding equation also for the V. We can say, okay, we want U0 because we want this condition at the wall for the U and the V, because in such a way we are in agreement with the observation that we observe that the velocity at the wall is equal to 0. And so we want to find something from the equation that we already know from our experience. Okay. Okay. I think it's more clear now. Okay, see you next week. Bye-bye.